Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll be learning a new concept which is extremely useful in solving problems involving more than one particle, and it is called center of mass. The first problem that arises without the concept of center of mass is how do you solve a problem of Newton's laws of motion in which you have a system in which the constituents are moving with different accelerations. For example, this is a standard problem we've seen before in laws of motion. I have two boxes, masses m1 and m2, and I want to find out the acceleration. So that's easy enough. For this, if this goes towards the right with an acceleration a, this comes down with an acceleration a. So let's say the tension is T, we'll have m2g minus T is equal to m2a, and T is equal to m1a. Right? So in those two equations, in the first equation we've taken m2 as the system, and in the second equation we've taken m1 as the system. Well, what if we want to take m1 and m2 both as a system? In that case, this T and this T would be an internal force, and this pulley would also have to be part of the system, but we don't know what to write on the right hand side. We can add up all the forces, but summation F is equal to the total mass. If we take both of them as a system and the pulley is light, it will be m1 plus m2 times a. But what would this acceleration be? It would not be the same as these accelerations. Let's say this is a1 and these are a. It would be something different, and if we knew what that was, then it would be a real convenience, because we would not have to choose systems in which all constituents have the exact same magnitude and direction of acceleration. So the ways with which we could solve a problem would increase tremendously. So for that, we introduce a concept called the center of mass, and for any system the center of mass is a very specific point which acts, as the name suggests, like the sort of center of the system, right? So for many practical purposes, you can assume that the system is a point mass situated at the center of mass. So let's say I have four particles, masses m1, m2, m3, m4, right? So using these four masses and the distances between the particles and the location of the particles, we will later see how to calculate the position of a very special point which will be called the center of mass, right? So it generally, for example, for a circular disk, it will lie at the center, right? For symmetric bodies and homogeneous bodies, it will lie at the center, right? The center of mass will be the center, but it will not always be the case. Let's say the center of mass is at this point. Then, for a lot of purposes, instead of taking these four individual particles as systems, because let's say their accelerations are in different directions, we can consider a particle situated at the center of mass, which has a total mass of m1 plus m2 plus m3 plus m4. We can't solve everything using this, but there are a lot of things such as momentum and using Newton's laws of motion and using concepts of work, energy and power, which become incredibly simplified if we just assume that instead of four particles at different locations, we have a single particle of mass m1 plus m2 plus m3 plus m4 at the center of mass, right? So we'll see the uses later. First step is to learn how to calculate the center of mass. So the definition of center of mass is this: it is a point which has coordinates x com is equal to m1 x1 plus m2 x2 plus dot 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 by m1 plus m2 plus dot dot. So we'll find the x, y and z coordinates of the center of mass separately, and once we have that, we'll have the position vector of the center of mass, right? So the x coordinate of the center of mass is simply the sum of m multiplied by x for each particle, the mass of the first particle multiplied by the x coordinate of the first particle, mass of second particle, x coordinate of second particle, and so on, divided by the total mass. It is also often written as summation I mi xi by summation I mi. I is basically just different particles. It's an index for different particles. So last time we had 4 particles. Let's just take that. So I have these 4 particles, m1, m2, m3 and m4. So I would go from 1 to 4. So I is 1, m1 x1, I is 2, m2 x2, m3 x3, m4 x4. We add them, and summation mi is basically the total mass. So it's also often written as summation mi xi by capital M. Capital M is nothing but the sum of the masses of the individual particles. That is the total mass of the system. Right? So let's just see a simple example. I have a one-dimensional straight line. This is the origin. I have a particle of mass 20 kg at x is equal to 4, and I have a particle of mass 10 kg at x is equal to 10. And I have only 2 particles. These 2 particles together make my system. Right? Where is the center of mass of this particle? Obviously the y coordinate and the z coordinate of the center of mass would be 0. By the way, y and z generalize just like this, right? So the y coordinate of the center of mass is 0 because the y coordinate of each one of them is 0. So y1, y2, y3 all are 0. Similarly for the z coordinate. For the x coordinate, we can see that the center of mass is at 20 times 4 plus 10 times 10 divided by 30. That is 180 divided by 30. That is 6. So x is equal to 6 would be the x coordinate of the center of mass. Right? So let's say this particle of mass 20 kg is moving in this direction with a particular acceleration, and this is moving in this direction with a particular acceleration. So instead of taking these two individually as a system, we can take them combined as a system, and we can assume that we have, instead of these two particles, an object of mass 30 kg at x is equal to 6, and reduces our two individual systems, to a problem in which we only have one system, and we can use it and we can analyze it to solve different quantities, right? So again, this is not true for everything. We cannot solve everything by this concept, but a lot of things can be solved by assuming that instead of 20 kg at 4 and 10 kg at 10, we simply have a 30 kg object at x is equal to 6, right? So the y and z formulas are similarly YCOM is summation mi yi by summation m, by m, or summation mi. ZCOM is equal to summation mi zi by summation m. Right? Now it doesn't matter where you take the origin to be. Right, so instead of this, let's say I took the origin, instead of at this point, I shifted everything and I took the origin at x is equal to 20, at x is equal to 6, right? My origin is at the 20 kg particle. In that case, XCOM would be 20 multiplied by 0, because now this is at x is equal to 0, right? So 20 multiplied by 0 plus 10 multiplied by 6. Because now this is not at x is equal to 10, this is at x is equal to 6, right? This will become x is equal to 0 and this will become x is equal to 6. We've shifted everything by 4, divided by 30. So that gives me 60 by 30, that gives me 2. So now it is at x is equal to 2, which is this point, if this point is x is equal to 0, right? 4, 6, 10. So again, if we have a system of many particles, we want to find the center of mass, we can take any point to be the origin, right? And we can find the position of the center of mass. The position of the center of mass will change depending on the origin. If this is the origin, this will be the position vector. If this is the origin, this would be the position vector. But the point where the center of mass is independent of the location of the origin which we choose. Because in both these cases, the center of mass was at a point which was in between these 2 points and divided this line in the ratio of 1:2. Right, so that will be true regardless of what you choose the origin to be. So this is for discrete system. Let's try to see a simple example. Three kg, 4 kg, 5 kg, and let's say this is 3, 4 and 5. I have three masses situated at the vertices of a right angled triangle, and I want to find the center of mass of this system. Without even saying anything, I can just see that the center of mass will lie somewhere within this triangle, right? So it doesn't matter what origin we take. The center of mass will be at the same point. The position vector of that point will depend on the origin though. So for the sake of convenience, I see that it's easiest to take this point as the origin. So if I take this point as the origin, XCOM will be 3 times 0, because the x coordinate of this is 0. The x coordinate of the 5 kg object is also 0, plus 4 times 4 by 3 plus 4 plus 5. So that will give me 16 by 12, which gives me 4 by 3. YCOM will be 3 into 0 plus 4 into 0, because the y coordinate of the 4 kg object is 0, plus 5 into 3 by again 3 plus 4 plus 5, which will be 12. So it will give me 15 by 12, which is 5 by 4. So we can see that the center of mass of this particle is going to be at a point which has position vector 4 by 3, 5 by 4. Right? So for a lot of purposes, we can just assume instead of these three particles at these separate points, we have an object of mass 12 kg at this point. And obviously that will make calculations somewhat simpler. Right. Now, not in every case will we have discrete objects, that is 10 different particles. Right? We might have a continuous system. So for example, instead of having 4 different objects situated like this, I could simply have a semicircular wire. Right. Now it has an infinite number of particles at an infinite number of locations, and we want to find the center of mass of this wire. I can see that the center of mass of this wire will lie somewhere at this point, right? It will not, if it was a complete wire, it would lie at the center, but since all the mass is at the top, it will be moved somewhat upwards. So in such cases, earlier what we did were discrete systems, now we'll be dealing with continuous systems. In continuous systems, all we do is, earlier we had summation mi by summation mi. Right, this is not true now, this was true earlier. So this goes to, in this case, so earlier we had, let's say, 4 particles of masses mi. Now we have infinite particles, but every particle has an infinitesimally small mass, right? If we had an infinite number of particles and each particle had a finite mass, the total mass would be infinite, right? So if we have an infinite number of particles, each particle has a small mass, let's call it dm, a very very small amount of mass, right? And this probably has, this dm particle has coordinates x and y and z, right? xi, yi, zi. Right, for this particular one, it will be different for each one. So we replace m by dm, but then dm into xi becomes a differential quantity, a very very small quantity. And how do we add very very small quantities? We don't sum them, we integrate them. So it simply becomes integral of xi times dm divided by integral of dm. Now integral of dm is obviously the total mass m. You take all the individual dm's and you add them up, you'll get the total mass m. So the denominator is the same, but instead of summation mixi, we have an integral of xi dm. Similarly, ycom is integral of yi dm, and zcom is integral of zi dm. Right. Actually, we don't need I now, because it is not for the ith particle. Every z corresponds to its own dm element. And what are the limits of the integration? The limits of the integration should be such that we take every single particle into account. We don't leave any particle out of the system, and we don't use any particle which does not belong to the system. Right. So that will become a little bit clearer with an example. So let's talk about this example itself. I apologize for the drawing. This is supposed to be a semicircle. Right. Semicircle radius is r, the total mass of the semicircle is m. Now this is not a semicircular plate, this is a semicircular wire, We'll do a semicircular plate next. Right now it's a semicircular wire. Right, so that means there is no mass within this wire. The only mass is at the extremities. So how do we take an element? There are many ways to take an element, but the important thing is, if you take an element, the x and y coordinate of the center of mass of the element should not differ much. So we can't take, if this is, let's say, a wire of finite thickness, for example something like this, we cannot take this small particle, this small element, a strip, as a system, because we would not know what to calculate as the x and y of this system, right? So an element should be such that its x and y are pretty much defined. They are not varied over a wide region of space. So one way could be, you take an element like this, an element which has a length dx and it is at a distance x, right? And you could find the center of mass of this element. You could integrate it to find the total center of mass, and the limits of x would be from x is equal to 0 to x is equal to pi r, because the length of this whole thing will be pi r if the radius is r. And you can try it at home and it works perfectly fine. However, an easier way is to do it in terms of angles. So I'll take the same element, but instead of dealing with x and dx, I'll deal with angles. So I'll take an element which is at an angle theta, and the angle it subtends is a very small differential d theta. Right, so this is my element. And now if I want to integrate it so as to take into account the complete semicircular wire, theta will have to go from 0 to 180 degrees, right? When theta is 0, I'm taking this element near this edge of the wire, and when theta is 180 degree, I'm taking it at this edge, right? So first thing to do is to calculate dm. What is dm? So that's easy enough. Dm will be the mass of this small element, which will be equal to the total mass divided by the total length pi r multiplied by the length of this element, right? Mass per unit length multiplied by the length. The length of this element is r d theta, right? That's sort of the definition of an angle, right? An angle is the length of this arc divided by the radius. So the length of this arc is the angle multiplied by the radius. R cancel and it gives me m d theta by pi. What are the x and y COMs of this? X is, this is also r, so x is r cos theta, and y is r sin theta, right? So I just integrate x dm and y dm, so that gives me x COM is integral of m by pi r cos theta d theta, of course divided by m, right? We have to divide it by the total mass, and the integral goes from 0 to pi, right? 2 pi is 180 to pi is 90. So m and m cancel. This gives me r by pi. Integral of cos theta is sin theta, right? Because derivative of sin theta is cos theta. So sin theta, limits are from 0 to pi, which is equal to 0, because sine of 0 is 0 and sine of pi is 0. So this gives me a result which I could have actually seen intuitively as well. Since this semicircular wire is symmetric along the in the x direction, that is, for every element we have in this point, we have another element in this point. So the x of this and the x of this cancel. So by symmetry, we knew that the center of mass had to be somewhere on this line. Right, so we find that the x of the center of mass is 0. By the way, when I say x is equal to r cos theta and y is r sin theta, I've implicitly taken this point as the origin, right? So we knew that it had to be on this line. If it had to be on the right, that would have implied that this right half of the semicircular wire is heavier than this left half. But that is not true, right? Similarly, y COM will come down to be, I'm not going to write this one, it's just sin theta instead of cos theta. The integral of sin theta is minus cos theta. So this will be r by pi minus cos theta 0 to pi. That gives me 2r by pi, right? Because cos pi is minus 1 and cos 0 is 1. So we found the result which we wanted to find out. If we have a semicircular wire of a radius r, this is the point where the center of mass is located. It is at a height 2r by pi, We know that pi is 3.14. This is obviously less than r, which is to be expected. This is at a height 2r by pi at the center in terms of the x coordinate. Right. So let's do one more quick example, an extension of this. How do I calculate the center of mass of a semicircular plate? Right. So now this is a semicircular plate. This is not a semicircular wire. I'll do this now. Before that, a very important concept is this. Let's say I have two systems. Right, this is my system 1 and this is my system 2. Let's say system 1 has a lot of particles in it. Maybe discrete or continuous, doesn't matter. System 2 has a lot of particles. Right. The center of mass of the total system will be, by the way, a notation which we use often is R of COM is simply summation mi ri, because summation mi ri is this vector, so the x component of the center of mass will be summation mi xi, and so on. This is just three vector equations. Right. Now we could write it as summation I mi ri plus summation j mi ri. I'll explain this in a second, by m1 plus m2. m1 plus m2 is the total mass, right? If we take this combined system, what we are trying to do is take this combined thing and find its center of mass. So m1 plus m2 is the total mass, that's fine. What I'm doing here is, instead of adding over all the particles in the combined system, I'm making I go through all the particles in this system and j go through all the particles in this system. So it still adds up all the particles. I've just separated the sum into two. It's like if you were adding from 1 to 20, you can say it as a sum of 1 to 10 and 11 to 20, right? It wouldn't make a difference. But what is summation mi ri? Summation mi ri is m1 rcom. R1 COM. What is R1 COM? The center of mass of this first system, because R1 COM would be summation mi ri by m1, right, over this system. Similarly, the second one would be m2 R2 COM by m1 plus m2, right? So, and what is m1 but this is the center of mass of a system in which we have an object of m1 and an object of m2 at a location R1 COM and at a location R2 COM. Meaning that if we want to find the center of mass of a composite system, instead of finding the center of mass directly, we can replace this system particle of the same mass at the center of mass. Let's say that is here, so we can just shrink this system to this point and we can shrink it to this point. And we can find the center of mass of these two. To find the center of mass of two particles is easier than finding the center of mass of two objects. Just a quick example of this, then we'll go back to this. You can try this with integration, but let me just tell you right now, the center of mass of a rod of length L is at the center. Right? If the mass is uniformly distributed, it is at the center. So let's say I want to find the center of mass of this composite system, which has two rods, both of the same mass, joined like this. So I could try to find this using integration and directly, but what I could do, which would be easier, is if both these rods have the same mass m and the same length L, to find the center of mass of the composite system, I can reduce this system to a particle of mass m at the center of mass, and I can reduce this system to a particle of mass m at the center of mass. So the center of mass of this composite system is same as the center of mass of this system, where you have two objects of mass m and m, and the center of mass of them will be at the center, so this point, which is at a distance of L by 4 from the vertex if the lengths are L. Right? So if we want to find the center of mass of a big system which has composite systems, we can assume that each system is simply a particle of the same mass at its center of mass. So now for the first time we see the use of one particular use of the concept of center of mass, right? And I'm going to use this thing to calculate the center of mass of a semicircular plate. So what I'm going to use is, we've already calculated the center of mass of a semicircular wire. So I'm going to assume this plate as a sum of a lot of strips, and my element would be this thickness is dr. So my element would be a semicircular wire of thickness dr at a distance r. Now you're gonna say that I couldn't do this in the previous case because what would be the x and y of the coordinates of this element? But now I know that because I want to find the center of mass of this composite system, I can assume that each of these strips is simply a particle of the same mass at a distance of 2r by pi. So I'm dividing this plate into strips and I'm assuming each strip is not a strip at all, it's just a particle of the same mass at the center of mass of the strip. Right? So again, x coordinate of the center of mass of each strip is 0. So x coordinate of the plate will be 0. To find the y coordinate, I'm going to do integral of dm. What will be dm in this case? It will be m by pi r square by 2 because the total area will be pi r square into what is the area of this strip? It is 2 pi r dr. Right? 2 pi r is this length and dr is this thickness. Excuse me. And because dr is very small, we can assume that this strip has a radius r throughout. So this will be dm. And we can say dm multiplied by, now if we were doing this originally, we couldn't have used a strip because what would be the y coordinate of the strip? It does not have a single y coordinate. But the center of mass of the y coordinate is a point and it has a coordinate which is 2r by pi. And r will go from 0 to capital R if this total radius is capital R. So you can put the value of dm from this point to this point and you can integrate and you will find the center of mass of a semicircular plate. Right? I'm not going to do it now. Similarly, you can find the center of mass of even more complicated objects. Try finding the center of mass of a cone. A solid cone and a hollow cone. Both of them will give you different answers. A hollow cone will be just the surface. The solid cone will be an actual cone which has material in it. Let's say a cone of radius r and a height h. You'll find the center of mass will be somewhere at this point at a particular height. You can find that. So now we've seen how to calculate the center of mass of a system in which two objects have different masses, have different accelerations. Right? Actually, that's not necessary for now, but the use comes in that case. So let's see the first example which we started from. So if this is m1, this is m2, the mass of the pulley is 0 because the pulley is assumed to be light. Right, so we take this combined thing as a system. The rope is also right, it does light, it doesn't have any mass. The center of mass will be somewhere at this point. But actually in this case, the center of mass is not really of use. What is of use to us is what acceleration should we use. Right, because we'll write all the forces that will be equal to m1 m2 times something. Right, so summation f will be equal to m1 plus m2 times a particular vector. What is that vector? That vector is related to this point center of mass, and in the next lecture we will see that it's actually the acceleration of this point. So if this point is the r coordinate of the center of mass, this object is moving towards the right, this is moving down. So because of that, the next instant the center of mass will not be at this point, it will be at some other point. So the center of mass will also have moved. Right? So if the particles are moving, then the center of mass is moving. If the particles have a velocity, the center of mass has a velocity. If the particles have an acceleration, the center of mass has an acceleration. And we'll see that this acceleration is actually that acceleration of the center of mass. For now, what you need to know is how to calculate the center of mass of any discrete object, or any discrete system, or any continuous system. We'll see the uses of this in the next lecture. Thank you.